In the last week of July 2026, 4 separate monitoring systems built by 4 separate branches of science on 4 separate continents moved into the same category at almost the same time. Nobody announced it together. No single broadcast carried all 4 stories side by side. A seismologist in Tokyo was not reading the same bulletin as a solar physicist in Colorado. A virologist tracking case counts in a WHO office had no reason to check a report on Atlantic Ocean currents. And yet, if you had pulled every one of those bulletins onto a single desk that week, you would have found the sky, the sea, the crust of the planet, and the human body all flashing the same color of alert, independently, within 72 hours of each other. This is not a story about a single catastrophe. There is no meteor bearing down, no ticking countdown, no secret memo leaked from a bunker. What actually happened is quieter and, in its own way, more unsettling. 4 warning systems, each built over decades, each designed to watch one narrow slice of the planet's behavior, all crossed a threshold in the same short window. And the honest, uncomfortable question that scientists are now sitting with is not whether one of these events is dangerous on its own. It is whether the timing means something. Start with the one that made international news within hours. On the afternoon of July 28th, the ground beneath Japan's southern island of Kyushu let go. A magnitude 7.1 earthquake tore through Kumamoto Prefecture, its epicenter shallow enough, only a few kilometers down, to turn a fault rupture into a citywide shock. A shopping mall partially collapsed. A paper mill chimney came down on workers inside. Roads cracked open. A cargo train derailed. Bridges buckled. The Japan Meteorological Agency, which runs one of the most sophisticated earthquake early warning networks on the planet, issued an advisory for a tsunami of about a meter along the Ariake and Yatsushiro seas within minutes of the shaking. 300,000 people were told to move to higher ground. By the next morning, at least 13 people were confirmed dead, with several more missing under the rubble of the mall and the mill. The tsunami advisory was lifted within 2 hours, a small mercy. But officials were careful to add something that rarely makes the headlines. Because the rupture was shallow, the fault system underneath Kyushu was primed for aftershocks, and residents were warned that the danger was not over, only paused. To understand why that warning mattered so much, it helps to understand what an aftershock sequence actually is, stripped of the ominous music that usually accompanies the phrase. When a fault ruptures, it does not release all of its stored energy in one clean instant. The surrounding rock is left in a state of altered stress, some sections pushed closer to failure, others temporarily relieved. Seismologists model this the way you might model cracks spreading through a pane of glass. The first fracture does not resolve the tension in the glass, it redistributes it, and smaller cracks often follow along lines the first one exposed. That is why the Japan Meteorological Agency's statement that the shallow depth of the Kumamoto rupture meant more earthquakes were likely in the coming days was not a vague gesture at uncertainty. It was a precise, physically grounded forecast built on the same statistical models used after every major shallow quake in a subduction zone. Kyushu sits in a region already threaded with active fault systems, and the government's decision to deploy thousands of self-defense force personnel within hours reflected an assumption baked into Japanese disaster planning for decades, that the first quake is rarely the whole story. While rescue crews were still working through the night in Kumamoto, 93 million miles away, the sun was doing something of its own. For years, forecasters have tracked what they call coronal mass ejections, enormous eruptions of magnetized plasma hurled outward from the sun's surface. Most arrive at Earth alone, spend a day or two rattling the magnetic field, and fade. But in the final week of July, NOAA's Space Weather Prediction Center watched something rarer unfold. 2 separate eruptions, launched a day apart from an unusually complex, energetically twisted sunspot region designated AR4494, began to merge in transit. Forecasters call this a cannibal CME, one faster cloud of solar material swallowing a slower one ahead of it, fusing into a single structure carrying more combined magnetic energy than either explosion on its own. The problem with a cannibal CME is not simply its size, it is its unpredictability. When 2 ejections merge, the internal magnetic orientation of the combined cloud becomes harder to model, which means the single variable that decides whether a storm is a minor nuisance or a serious problem, the north-south tilt of its magnetic field, becomes almost impossible to forecast until the storm is already washing over the planet. NOAA issued back-to-back geomagnetic storm watches through the final days of July, warning of G2 and potentially G3 level storms, strong enough to induce voltage irregularities in high-latitude power grids, degrade GPS and high-frequency radio, and push the aurora as far south as the northern United States. Scientists studying the sun's current cycle noted that even though the sun passed its statistical peak of activity back in late 2024, the surface was still producing complex, high-energy regions capable of this kind of layered eruption, and that the following year would likely remain a period of elevated risk for satellites and grid infrastructure. It is worth sitting with why a cannibal CME unsettles even veteran forecasters more than a routine solar storm. A single, isolated coronal mass ejection behaves in a way that decades of observation have made reasonably predictable. Instruments can estimate its speed, its likely arrival window, and a rough sense of its magnetic orientation before it reaches Earth. A merged structure breaks that predictability. Two separate magnetic fields, each internally consistent, collide and reorganize into something new. And the physics of that reorganization are turbulent enough that the resulting orientation, the single factor that decides whether a storm glances off the planet's magnetic shield or couples into it forcefully, cannot be reliably forecast, until the leading edge is already sweeping past monitoring satellites stationed roughly 1 million miles from Earth. Researchers studying the planet's magnetic response have been explicit that if there is no firm upper limit to how strongly the magnetosphere can be driven by an extreme event, then models built only around historically observed storms may be underestimating the tail end of what is physically possible. That is not a claim that a Carrington-scale catastrophe is imminent. It is an acknowledgement that the confidence forecasters normally have when tracking a single ejection evaporates the moment two of them merge, and that evaporation of confidence, more than the storm's raw strength, is what pushed this event into a different category of watch. Meanwhile, a warning system with a much longer memory was also flashing. This one does not measure a single event. It measures a slow accumulation, the kind that resists the instinct to treat a single week as a headline. Climate scientists refer to it as the monitoring of tipping elements, the handful of Earth systems large enough and interconnected enough that if pushed past a certain threshold, they do not simply degrade gradually. They flip rapidly and, in most cases, irreversibly. A major scientific review published earlier this year, building on work from the University of Exeter, the Potsdam Institute, and other partner institutions, concluded that as many as 8 of these tipping points could now be triggered even if global warming stays below 2 degrees Celsius, a threshold once treated as a relatively safe outer limit. The Atlantic meridional overturning circulation, the deep ocean current system that moves warm water north and helps regulate the climate of Europe and the monsoon patterns of Africa and Asia, is now measured at its slowest point in 1,600 years, and recent modeling in a leading academic journal suggested its decline is running well ahead of the projections that international climate bodies have relied on. Beneath the Arctic tundra, permafrost holds roughly twice as much carbon as currently sits in the entire atmosphere, and researchers running millions of computer simulations found that in about a third of tested scenarios, a chain reaction begins. Warming melts permafrost. Permafrost releases methane. Methane accelerates warming, and each step makes the next one more likely. A separate assessment led by Oregon State University researchers, examining 16 of these tipping elements together, described the risk of a so-called hothouse trajectory, a state in which feedback loops compound faster than any single policy response can counter. None of this is a single dramatic image. There is no live footage of a tipping point being crossed, but the monitoring systems built to detect early warning signals in the Greenland ice sheet, in the Amazon rainforest, and in that Atlantic current have all reported the same thing this year. Signals consistent with systems approaching, not retreating from, their thresholds. The reason scientists reach for the word tipping point rather than simply saying a system is degrading is that these systems do not respond to stress the way a dimmer switch responds to a hand turning it slowly. They respond the way a light switch does. For a long stretch, a stressed system can absorb additional pressure while showing only gradual, almost linear change, the kind that looks manageable on a graph. But past a certain threshold, the same system can flip into an entirely different state abruptly, and in most of the cases, climate scientists study, that new state is effectively permanent on any timescale that matters to human civilization. A coral reef does not slowly fade from vivid to pale over decades in a straight line. It can collapse within a single unusually hot season once thermal stress crosses a biological limit. Ice sheets do not melt at a constant rate. Once meltwater begins lubricating the base of certain glaciers, the flow toward the ocean can accelerate in ways that are extremely difficult to model and even harder to reverse. This is precisely why the monitoring infrastructure built around these systems focuses so heavily on what researchers call early warning signals. Subtle statistical fingerprints, increased variance in temperature readings, slowing recovery times after small disturbances that tend to appear in the data before a system actually flips, the way a bridge might begin to hum at a different frequency before a structural failure. Detecting those fingerprints early is the entire point, because once the flip itself is visible on the news, the option to prevent it has usually already closed. And then there is the fourth system, the one built not to watch rock, plasma, or ocean currents, but the human body itself. Global health monitoring agencies maintain a category they call Disease X, a deliberately unnamed placeholder for a pathogen that has not yet been identified, but that the surveillance architecture is built to catch early. It is not a prediction of a specific outbreak. It is an acknowledgement that the most dangerous future pathogen is, almost by definition, one nobody is watching for yet. What made this particular window notable is that health researchers monitoring zoonotic spillover, the process by which a virus jumps from animals into humans, flagged 4 pathogens simultaneously moving in the wrong direction. Mpox continues to circulate in multiple countries, including new strains appearing across parts of Europe. H5N1 avian influenza remains under close watch by epidemiologists concerned less about the virus in its current form and more about the possibility of it acquiring the ability to spread efficiently between people. Rubella, a disease many public health systems considered a solved problem, has resurfaced in populations where vaccination coverage has quietly fallen. And Oropouche virus, nicknamed sloth fever after the animal reservoir it was first identified in, produced its first confirmed cases in parts of Europe last year after spreading through mosquito and midge populations in South America. None of these 4 pathogens is, on its own, disease X. But global health officials have been explicit that the underlying trend, declining vaccination rates, weakened surveillance funding, and diagnostic gaps identified in a major assessment released this year, is exactly the kind of environment in which an unidentified pathogen could spread undetected for critical early weeks. The mechanism behind a zoonotic spillover event is, in its own way, as mechanical and unglamorous as a fault line redistributing stress or a magnetic field, reorganizing in transit. A virus that circulates comfortably in an animal reservoir, a bat, a bird, a rodent, a pig, is usually poorly adapted to human biology. Every so often, through sheer replication volume, a random mutation lets it bind more efficiently to human cells, or spread more easily through human respiratory droplets, or survive longer outside a host. Most of these mutations lead nowhere, evolutionary dead ends that fizzle out within a single infected household. But the more opportunities a virus has to jump into humans, and the more humans it then has the chance to replicate inside, the more rolls of that genetic dice occur. This is precisely why epidemiologists are less alarmed by any one of the 4 pathogens currently on the watch list, and more alarmed by the conditions surrounding all 4 at once. Closer human contact with wildlife reservoirs through land use change, denser urban populations that let a virus circulate faster once it arrives, and, critically, a surveillance and vaccination infrastructure that, in several countries, is measurably weaker than it was 5 years ago. A well-funded, well-staffed surveillance network does not prevent spillover from happening. Spillover is a near-constant background process in nature. What it does is catch the spillover in its first days rather than its first months. And that difference, historically, has been the difference between a contained local outbreak and a global emergency. So here is the honest shape of the story. 4 systems. A fault line under Kyushu, a sunspot region on the solar surface, an ocean current slowing in the North Atlantic, a surveillance network watching viral chatter in animal populations. None of them caused the others. There is no physical mechanism by which an earthquake in Japan influences a coronal mass ejection, and no chain of causation running from permafrost methane to bird flu. Correlation is not causation, and any script that tried to claim otherwise would be lying to you. But there is a reason scientists across completely unrelated fields have started using the same word to describe what they are watching, and that word is convergence. Here is what convergence actually means, mechanically, once you strip away the drama. Every one of these 4 systems is, at its core, a monitoring problem. Humanity did not build early warning networks because these events are new. Earthquakes have shaken Japan for millions of years. The sun has thrown plasma at Earth since before life existed. Viruses have jumped species since the first animals evolved. Ice ages and hothouse periods came and went long before anyone was measuring them. What is new, historically speaking, is our capacity to detect all 4 in near real time, and to recognize when they cluster. A century ago, the Kumamoto earthquake would have been a regional disaster, reported with a delay of days, its scale understood only locally. A geomagnetic storm would have simply appeared as strange auroras and unexplained telegraph failures, as it did during the Carrington event of 1859, with nobody able to say why. A slow ocean current shift would have gone entirely unnoticed for a generation, since nobody had the instruments to measure Atlantic circulation at all. And a virus jumping from an animal reservoir into a small rural population might never have been detected until it had already spread widely. Today, all 4 are visible almost as they happen, cross-referenced by international networks that share data across borders within hours. The paradox is that the more sophisticated our warning systems become, the more capable we are of noticing when several unrelated stresses line up in the same week. And the more that lineup feels, psychologically, like the planet itself is sending a signal, even when the honest scientific answer is that we are simply better at listening than we have ever been. That does not mean the individual risks are small. Consider what each of these systems is actually protecting against, described plainly rather than dramatically. The tsunami warning system that activated for Kyushu exists because Japan sits atop one of the most active subduction zones on the planet, where the Philippine Sea Plate grinds beneath the Eurasian Plate. And a shallow rupture like the one on July 28th can trigger genuinely destructive waves within minutes, faster than most evacuation routes can clear a coastal population. The geomagnetic storm watch exists because modern civilization runs on systems that a Carrington-scale event could seriously damage. High-voltage transformers that take months to replace if overloaded, GPS-dependent aviation and shipping navigation, and satellite constellations, including the low-orbit internet satellites that now carry emergency communications for remote regions. The tipping point monitoring exists because a collapse of the Atlantic circulation would not simply mean a colder Europe. It would mean disrupted monsoon rainfall across regions that feed hundreds of millions of people, and a permafrost feedback loop, once it fully engages, cannot be switched off by any subsequent policy, no matter how aggressive. And the pandemic surveillance system exists because the last pathogen that emerged from an animal reservoir with no name and no vaccine cost millions of lives and trillions of dollars within a single year. And every epidemiologist working in this space will tell you plainly that the next one is a matter of when, not if. What shifted this particular week was not that any single one of these thresholds was crossed catastrophically. It is that the alert level in all four systems rose together, and the scientists running each individual system were forced to answer, publicly, a question that used to sound almost like science fiction. Are these problems increasingly likely to arrive stacked rather than one at a time? Analysts studying global systemic risk, the field that tries to model how failures in one domain strain the capacity to respond to failures in another, have started describing this as cascading risk. A geomagnetic storm that knocks out regional power infrastructure the same week a major earthquake forces mass evacuations does not simply add two problems together. It multiplies the strain on emergency services, on communication networks, on the people whose job it is to decide where scarce resources go first. A climate system inching toward a tipping point does not exist in isolation from a pandemic surveillance network stretched thin by funding cuts. Both draw on the same finite pool of trained epidemiologists, satellite bandwidth, and international coordination capacity. The four warning systems that lit up together this week are not four separate stories that happen to share a calendar page. They are four instruments measuring different parts of the same underlying fragility, a planet and a civilization built on top of it that is more interconnected and more closely monitored than at any point in human history, which means both that we see danger earlier than any generation before us, and that the danger, when it does gather, gathers across more fronts at once. There's a useful, if uncomfortable, comparison from outside science entirely. The way modern hospitals monitor a critically ill patient. A single elevated reading, a slightly high heart rate, a mild dip in oxygen, rarely triggers alarm on its own because human physiology has enough redundancy to absorb small disturbances without real danger. What actually causes a rapid response team to be paged is when several vital signs drift into concerning territory at the same time, because the body's capacity to compensate for one problem depends on the healthy functioning of the others. A planet's monitoring systems, in a rough and imperfect way, work on a similar logic. A single elevated fault stress, a single complex sunspot region, a single slow ocean current, a single circulating virus. These are things the systems that support 7 billion people have absorbed before and will absorb again. What draws sustained attention from people who study systemic risk professionally is not any one reading. It is the shape of several readings drifting in the same direction inside the same short window, because it is precisely in those windows that the capacity to respond to any single event is most likely to be stretched thin by all the others competing for the same emergency responders, the same satellite bandwidth, the same international coordination meetings, the same news cycle, and the same public attention. None of the scientists behind any of these four systems are predicting collapse. That distinction matters enormously, and it would be dishonest to blur it for the sake of a more dramatic ending. The Japan Meteorological Agency's aftershock warning is a standard, responsible caution issued after every shallow major earthquake, not evidence of an imminent larger event. NOAA's geomagnetic storm watches are routine forecasting products, refined over decades, designed to give power grid operators and satellite controllers enough lead time to take protective action, not a warning of civilizational danger. The tipping point researchers are explicit that every fraction of a degree of warming avoided measurably reduces the odds of triggering these thresholds, meaning the outcome remains, in their own words, not yet fixed. And the WWHO's Disease X framework exists specifically so that if an outbreak begins, the world has systems, vaccine platforms, and diagnostic tools ready before the pathogen even has a name, rather than scrambling to build them from nothing the way the world did in the early months of 2020. These are functioning safety systems, doing exactly the job they were built to do. The story is not that they failed. The story is that they all had to work at the same time. It is also worth naming, honestly, what these systems owe their existence to, because none of them arrived by accident. The tsunami warning network covering the Pacific was built and repeatedly upgraded after earlier disasters exposed exactly how many lives are lost in the gap between a rupture and a coordinated evacuation. The space weather monitoring infrastructure exists largely because of hard lessons from earlier storms, including outages that knocked out satellites and disrupted power grids decades before this one, lessons that convinced governments an early warning of even a few hours was worth the enormous cost of dedicated monitoring satellites parked between the Earth and the Sun. The Climate Tipping Point research program grew directly out of the recognition, only fully accepted within the scientific community in the past 2 decades, that treating warming as a smooth, gradual process had led policymakers to underestimate how abruptly certain thresholds could be crossed. And the entire architecture behind the Disease X concept was essentially forced into existence by the last pandemic, a direct institutional response to how unprepared the world was for a pathogen with no name and no existing countermeasure. Every one of these 4 systems, in other words, is a monument to a previous failure. They exist because something went wrong before they did, and enough people insisted afterward that it should never go unwatched again. That history matters because it means the alarm sounding in all 4 systems this week is not a sign that humanity has grown complacent. It is closer to the opposite. It is the sound of institutions built specifically to notice things doing exactly what they were designed to do, at the exact moment they were designed to do it. What happens next is genuinely unknown, and any script claiming certainty here would be inventing confidence that does not exist. The aftershock sequence under Kyushu could taper off within days, or it could produce another significant rupture along a fault system officials have already called primed. The cannibal CME merging above Earth this week could pass with nothing more than a striking aurora display over northern latitudes, or its unpredictable magnetic orientation could tip toward the configuration that causes real grid stress, something forecasters will only know for certain in the hours before impact. The Atlantic circulation could continue its measured, decades-long decline within the range current models describe, or new data could reveal it is closer to a threshold than anyone currently estimates, the way earlier tipping point assessments have already had to be revised once new evidence came in. And the 4 pathogens, under closest watch by global health authorities, may simply continue as background concerns, managed the way seasonal outbreaks usually are. Or one of them could be the thing epidemiologists have spent a decade preparing an empty file labeled Disease X to receive. What is certain is only this. For 1 week at the end of July 2026, 4 instruments built on 4 continents by 4 separate scientific communities, speaking 4 different technical languages, all reported the same underlying message in their own vocabulary. The ground is not still, the sun is not calm, the ocean is not steady, and the boundary between human and animal disease is not as fixed as it once felt. Whether that message means the planet is entering a genuinely more volatile period, or whether it simply means our instruments have finally become good enough to notice what has always been true, is a question the data from this single week cannot answer. There's a version of this story that ends with reassurance, and a version that ends with dread, and the honest answer is that neither is fully earned yet. The reassuring version points out, correctly, that every one of these 4 systems has weathered comparable stress before without producing the outcome people fear most. Japan has absorbed shallow major earthquakes along this same fault architecture for centuries, and rebuilt every time. The sun has produced complex, high-energy sunspot regions throughout every solar cycle on record, and the overwhelming majority of them have passed the planet with nothing more than a striking display of aurora. The Atlantic circulation has slowed and partially recovered across long stretches of the paleoclimate record, long before any human activity could have influenced it. And every prior scare involving an animal origin virus, save one, has been contained by exactly the kind of surveillance system that flagged this week's 4 pathogens in the first place. The dread-driven version of the story points out, just as correctly, that past resilience is not a guarantee of future resilience once the underlying conditions change, that a fault system, which has always produced manageable earthquakes, is not thereby incapable of producing a larger one, that a sun in decline from its statistical peak is still measurably capable of extreme behavior, that an ocean current can decline gradually for centuries, right up until the point where gradual decline gives way to abrupt collapse, and that surveillance systems only catch what they are funded and staffed well enough to catch. Both of these framings are using the same data. Neither is lying. That more than any single alarming figure buried in any single agency's bulletin is the real discomfort sitting underneath this story. The same set of facts can be read as evidence that the systems are working exactly as intended, or as an early glimpse of a planet whose margins are narrowing in more places than one at a time. The instruments cannot resolve that disagreement for us. Only what happens in the weeks and months that follow will. For now, the warning systems will keep watching, each in its own narrow language, largely blind to what the others are reporting on any given day. Whether anyone is watching them closely enough, together, across all four fronts at once, before the next convergence arrives, is the part of this story that has not been written yet.